I have the pleasure of introducing our speaker. Is that working? Do I need it? I probably don't need it. I have the pleasure of introducing our speaker today, Juan Ignacio Collar.
Seriously.
On the 4th of August, 1964. You know, I knew he was going to try this because I went and watched some of his YouTube. And every YouTube where he's being introduced as a speaker, as the person's introducing him, he's coming up to the stage. So, but I'm going to keep going.
Okay, yeah, let's go for it.
So Juan got his undergraduate degree in Madrid. He went to the University of South Carolina. He was a postdoc in Paris and at South Carolina. He was a fellow of the experimental division at CERN, a Marie Curie fellow at the University of Paris. This guy really gets around.
Mercenary of science.
Might be a terrorist. Came to the University of Chicago in 2001. Juan is very hard to capture. He is a very dear colleague, but he's hard to capture. So I thought I would go to his own words. It's hard to introduce. So many of you think of him as the coffee czar, getting emails like this, coffee maker is kaput. Spent a couple of hours this morning trying all the tricks, and so on and so forth. Some of them are good. The coffee maker is back, enjoy. That's not today, that was a year ago. But for me, you know, his talks are great. You're going to find that out eventually. His own words are fantastic. So this is on his KICP website. My main interest is in the development of innovative methods for the detection of hypothetical astroparticles, WIMPs, axions, magnetic monopoles, any yet to be discovered component of cosmic rays that might constitute a fraction of the dark matter. Needless to say, this is a risky business, but I am equally interested in the journey and the destination. This is poetry. The extreme levels of sensitivity required. I knew I should have turned that microphone. And some of these experiments force us to devise new detection technologies, which is really a hallmark of what Juan does, in an endless quest for the better mousetrap. It is a very enjoyable challenge. And I also decided to capture him, to ask his colleague, because I know his colleagues think very highly of him. So, for example, Luca. Juan is a great mentor. That's pretty good.
That's okay, I have to say.
But I confess, well, there's more. But I confess that seeing an old picture of him in his house, showing Juan 20 years ago on the stage posing as a bodybuilder and wearing a very skimpy Speedo was one of the most horrifying experiences of my life.
The posing trunk.
But let me just, I want to finish up with two that really capture Juan the scientist. And the first is from Andrew Sonnenschein.
Oh.
And he said, of course, the thing that stands out about Juan is his enormous creativity, and I agree with that, I can even tell. He comes up with at least a half dozen interesting new ideas for dark matter or neutrino detection experiments every year. And one or two of them actually turn out to be practical to do, which is a high ratio in this business. And then Nigel Smith, the director of Snow Lab. You'll get to speak in a second. I can see I quieted it down there. One continually looks for new new opportunities in research, thinking outside standard approaches and applying these ideas to move the field forward. Time with Juan is never dull.
Okay.
As he's always passionate about his work and his life. Juan Collar, tell us about PICO.
Okay, thank you. That was quite the introduction, and you stepped on my joke because I was going to say that you might as well save us some time and introduce me as the coffee maker repairman, because that's, in any case, was taking most of my time these days. I take the opportunity to remind you that I'm watching you. Anyway, so last year, Andrew, one of the people who betrayed me a minute ago, Andrew was here giving you a talk on PICO, so I figured that rather than tell you again about the wonderful things about bubble chambers, etc., I'm going to go very, very lightly on that and then tell you about future plans and latest news. And then I, based on the same line of thought, I said, well, why don't I tell them about something they haven't heard about yet, which is Coherent. And then I tried to develop some lame excuse for a glue between the two. And you have read that in the abstract. I don't know how well that's going to work out. But anyway, so PICO bubble chambers that we used to look for weak dark matter are revisiting an old technology, and we are actually able to make them work like the old bubble chambers that used to work by insisting in heating them up to the point that something's going to break. That's the panel on the left. And then we can see these rather muscular tracks in our case because our triggers are slow, not as fast as they used to be in the older days, from minimum ionizing particles. And those are precisely the ones we're not interested in seeing. This is a muon just zooming through the chamber and creating, you don't want to see the next few frames, but creating a trail of distraction in there. We cannot recompress the chamber fast enough at this temperature to avoid that. So we don't run them like this. We run them at lower degrees of superheat, in this case expressed by a lower temperature, where the only particles that can give us events in there, bubbles, are nuclear recoils, like those we're looking for from wind interactions. And we have an additional tool in our bag, which is the high spatial granularity, the fact that we can see very well with faster newer cameras, we can essentially spot these bubbles when they appear, when they're sub-millimeter in size, and then clearly this is not a WIMP, because there's a fat chance, because they don't exist, I was going to say, but because there's a fat chance that they that you will get ever more than one interaction from a particle with such a small cross-section, right? So we know that's a neutron, and this might be a WIMP. We wrote a bunch of papers about the changes we had to make to get to the point we could use them to look for the matter. That took a lot of blood, sweat, and tears. Blood, sweat, and tears from mostly all of our KICP graduates. We got Andrew Sonnenschein. Actually, he was one of the first year KICP fellows. Alan is a recent graduate student, now a postdoc at Fermilab, and then we have junior faculty members in Northwestern and in Drexel, and these two people have been as well KICP fellows. I'm going to tell you, my very last transparency is actually about the work by Eric. Eric studied there. This is taken this summer in one of our collaboration meetings right here. So the reason why the physics behind what I just expressed there is the fact that there's two thresholds, and this is a theory we didn't have to invent. This is a theory referred to as the Sykes model of bubble nucleation in bubble chambers. And this has been around for decades. And it tells you that in order for you to form a bubble in a bubble chamber, you need to surpass two thresholds. One in a minimum energy deposited by the particle, and the other one, this is key for us, in stopping power. If you don't concentrate the energy high enough in space, then the diffuse heat is no good to produce bubbles. So we mess with the thermodynamics, we choose convenient temperatures and operating pressures in such a way that we can sense nuclear recoils, or unfortunately we have to accept alpha particles and alpha recoils, but not any of those minimum ionizing particles, even at the end of the range when the stopping power is maximum. So in other words, anything in the top right quadrant here can produce bubbles, elsewhere you cannot. And this is the threshold in stopping power, and this is the threshold in minimum energy. So we can dial in several different levels of sensitivity. As you can see, we can change the threshold. This is a threshold device, meaning that a particle surpassing the threshold will produce bubbles. We don't know if the energy was 10 times larger than the threshold or just barely. In order to do that, we have to change the threshold. So if we ever see WIMPs, we have to run at two different temperatures, for instance, or two different pressures in order to determine the mass of the WIMP, but that's no big loss. Now, this is probably the plot that tells the story best about what, in my opinion, is the very best feature of our bubble chambers. The fact that we have the best electron recoil rejection of any WIMP detector. Electron recoils are produced by gamma interactions, environmental gammas, and are essentially the abatement of those is where all of the effort goes by others in the field. In our case, because of this, the fact that this is outside of that top right quadrant, as I mentioned, in our case, we have an intrinsic insensitivity to those that is rather brutal. For instance, the bubble chamber or the run that I will just show you in a few minutes, the last run from PICO 60, the chamber was operated at 3 kV of nuclear recoil threshold. And you can see that we almost have 10 to the 10 discrimination against gammas or electron recoils. It takes 10 to the 10 electron recoils or gammas interacting before we see a single bubble from those. So we don't have to move a finger to reject those events. They just don't appear. You don't see bubbles. It depends on the compound we put in the bubble chambers. These are the two we have used thus far. There are reasons that we understand on why this is different. It has to do with the binding energy of electrons around iodine and fluorine. And you can see immediately that it's advantageous to go to this one because you can reach a much lower threshold, much lower sensitivity or better sensitivity to nuclear recoils while still enjoying that beautiful rejection of electron recoils. They are highly scalable. What's really nice about a bubble chamber is that you are monitoring the whole volume with a single channel. We can either just look at what's happening with fast cameras, or we can listen to the sounds produced by these bubbles, the rapid expansion of these bubbles, as I'll tell you a lot about in a minute. Or being a closed system, you can just have an AC coupled pressure sensor and see the rapid increase in pressure produced by the growth of a bubble. And we actually typically have the 3 triggers monitoring, but the cameras do the best job. So it's very easy to just scale things up in that sense. The amplification of the event is given by Mother Nature. The bubble just grows. Unless you do something about it, it will just keep growing. So we don't have to move a finger to amplify it. We have a very good, actually the best sensitivity to spin-dependent couplings, and this is for reasons of the nuclear structure of fluorine. I'll show you something about this briefly in a minute. And what I already mentioned, high spatial granularity, low cost, room temperature operation. We use safe refrigerants. This one, by the way, is so safe that it's actually biocompatible. They actually inject into your eyeball after or during surgery. So, you know, it's stuff that doesn't make anyone at Snow Lab worry too much about what we're doing in there if we were to have an accident or anything like that. It's not the old days of the hydrogen bubble chambers or anything like that. So I mentioned that we listen to the sounds produced by the rapid expansion of these bubbles. Actually, I should say proto-bubbles because as you will see, we reach out in frequency quite a bit, and that means that we reach out back in time to the early stages of development of the bubbles. When they're pretty tiny, sub-micron, they're producing sounds that we are already capturing. And we capture those with piezoelectric sensors. Back in the day, when Glaser was messing around with his early bubble chambers, being the inventor of them, he knew about these sounds. He called them plinks. And that's a very good choice of words because that's exactly how it sounds. If you listen to these things and they're audible, they're very high pitch. So he would register those with a phonograph pickup that would trigger the photography. Now we have piezoelectric sensors that we make out of radio clean ceramics. That took a lot of work to get to the point that these were not neutron sources of their own right. And you can see some traces there. We can register sounds that way. Some 20, 30 years ago, 20 years ago, I read a paper by some crazy Russians. This is written in one of my favorite journals, which is an incredible source of inspiration, where they predicted that you should be able to use acoustics in bubble chambers to identify particles, and I thought it was insane. But I'm going to show you how sophisticated this signature is in a second. Our colleagues within PICO, the P for PICO comes from this side of the collaboration, mostly Canadian, were the first ones to notice that indeed there seemed to be a difference in loudness between the acoustics or the acoustic emission coming from an alpha particle and a nuclear recoil that you can induce in there, of course, with a neutron source. And the technique has been developing to the point that it's just gorgeous physics. We're doing, for instance, acoustic calorimetry. We can tell the energy of an alpha particle. When we started, we had just a single bump And nowadays, we can tell that this is a 6 MeV alpha and that's an 8 MeV alpha. We of course have an external handle to tell us which is which. These things follow decays in radioactive chains. And we see that indeed the louder ones are 8 MeV and the windier ones are 6 MeV. That's where the nuclear recoils appear, and it's a logarithmic scale, when we calibrate with neutrons. But we've grown in knowledge, in investigations about this acoustic signature. What we're noticing, for instance, these days, is that even, it's not just the loudness, it's the tone. There are very characteristic differences in frequency, in power across frequencies for these two alpha particles of a slightly different energy. So we are hoping, and you will understand why in a minute, to keep pushing this technique to the point that we can differentiate between electron recoils and nuclear recoils. You're probably wondering why do they want to discriminate electron recoils if he just showed us 10 to the 10 discrimination. Well, the reason is this: if we want to lower our threshold, see how fast that grows. If we want to go to say 1.5 kV, we have lost several orders of magnitude in intrinsic rejection. If we're able to compensate for that by coming up with some acoustic rejection, we're golden. We can keep pushing towards lower wave masses, where the lower you go threshold, the smaller the recoil energy you can expect to see. And this is actually an area of interest for me. I mean, I'm really fascinated by the acoustics, and we're starting to build the moment my laboratory reopens this summer. I was told 13 months, it's been 17, but anyway, so nobody responsible for this is in the room, so I'm not pretty sure. Anyway, so whenever we reopen, we're building a calibration chamber to actually investigate what's happening at higher frequencies. We don't have any sensitivity here above a few hundred, well, actually the order of 100 keV in present chambers, and this has to do with the present design of the piezo's, the geometry of the ceramic, and also cutoffs in our amplifiers. So we want to push by perhaps an order of magnitude a bit more before attenuation becomes a problem. These refrigerants we use in the chamber are very elastic, and therefore the attenuation of high frequencies is about 100 times higher, unfortunately, than in water, for instance. So eventually we don't have a chance of picking up a signal, half a meter away from a bubble. But this is, as I said, going backwards in time, where we think we might see these differences between electron recoils and nuclear recoils. So this is fascinating stuff, and this is actually a figure from the KICP proposal. The price is high. If we can push down in threshold, then we'll be doing much better at low wind masses. I should say that there is a passive way to improve our sensitivity. Before I forget, because I will forget later on, one thing we can do, besides pushing on the acoustics, is just simply shield better against these gammas. We know that we're dominated by gammas coming from the environment. The levels of radioactivity inside the chambers are actually very, very small. Carbon-14, all that stuff is very, very tiny. So right now we have chambers that are sitting in essentially a small water bath, 1 meter in radius, just enough to moderate neutrons. But when we move to the new tanks that I'm going to show you already existing in Snow Lab, we'll have 3 times more water, and that on its own, the simulations are being performed as we speak, could be enough for us to actually take this bigger bite to lower wave masses. But anyway, that's one of our areas of emphasis. Something we've been doing here recently too is
which is really the path of the gamma of 1 MeV unit order of.
Oh, it depends on the gamma energy, but
yeah,
order of a few centimeters. But remember, even if the gamma interacts several times, even if you lower the threshold, you still have a 1 in 10 to the 6 chance of seeing one of those.
I was just wondering, can't you visualize, since you see where the bubble is, you can remove the outer.
You could do that too in larger chambers. Yeah, even for neutrons as well. But the chambers right now, 50 kilos, you still don't want to do that. But when we move to PICO 500, that would be a possibility as well. Yeah. So we've been using neural networks. This was actually a bit of a desperate attempt. I'm going to describe the last run, and I'm going to tell you the wonderful results. And I might as well tell you about the tragedies of this run right now. We started with 8 PSOs that have been tested in an environmental chamber, cycled in pressure and temperature. They were working fine when the chamber was put together. We fill up the tank, we turn on the experiment, 6 PSOs are dead. So we limped along and were able to get our latest result with just 2 out of 8 PSOs working. So in a rush, we developed this neural network that is doing so much better than what we call the acoustic parameter, this human attempt as doing things acoustically. The neural networks are, to me, after working with them, they're really the shape of things to come when it comes to finding these small, subtle patterns in frequency that I showed you before. So I think several of us are convinced that this is the future for us, and it's lots of fun too. So the latest results. We had some problems, as you know, in the past with particulates. Those were resolved. I think Andrew told you all about that the last time he was here, so I won't repeat that. And then after a best effort to solve the problems, finding the causes first and then solving the problems, we ran again. I have already shown you the opening of the box. It's actually this plot here, this quadrant down there that contains calibration, neutron-induced recoils. These are the physics run events, and as you can see, there's no events in there. We ran a blind. For the first time, we felt like we knew enough about the chamber to run blind. We took data for a month, prescribed a period, and when we opened the box, zippo. This is incidentally, at the scale of these experiments, probably the first time it happens. We are not lagging behind from with the possible exception of Xenon 1 ton, but certainly for LUX, the fiducial volume, I believe, is 100 kilos, correct me if I'm wrong. This is almost 50 kilos. And in liquid xenon experiments, typically you find some events in the box, in the nuclear recoil box. We had 0, or actually 3, but you'll see how they look. And those are the 3 events, evidently no loops. Okay, so this is the advantage of having high granularity. 3 neutrons managed to get in there. We expected 1, we got 3. It's not a big disagreement, certainly with all that goes into the simulations. And clearly they were excluded as linked interactions because of the multiplicity. And these are the results. We were leading already in spin-dependent couplings, and we took a big jump by a factor of 17. These are supersymmetric models. People often plot these things, essentially where the phenomenologies are telling us to look. They keep changing the blob, of course, as we march along. It's the eternal carrot at the end of the stick. But this is where we are right now, and I'm going to make a few remarks about this. The first one, these are plots that some people locally, I think Nicole has done a lot of work in this area, but these are predictions by these effective field theories that tell us that in that framework, if you think along those lines, there's essentially 2 couplings that belong to PICO. This is a figure of merit that tells you how well you expect to be in interactions with protons. So that's how we do so well. But what I want to emphasize is that we're not a boutique experiment aiming only to look for this coupling, 2 out of 6, however many there are nowadays. I'll show you a bit more about that. We're really comparable to liquid xenon experiments in our probing of supersymmetric models. I'll show you in a couple of slides. This is news from last week. John Beacom called my attention to this paper, and I figured I would publicize it. So you see that here we have limits from indirect searches, right? From looking at the sun and trying to look for the annihilation products of the winds that could be trapped in there, in the sun. What John and his collaborators have written about recently is the fact that these experiments, indirect searches, are about to run into their own neutrino floor, as we call it, in this case from interactions of high energy cosmic rays in the solar atmosphere. And essentially about an order of magnitude from where they are right now, they will run out of gas. They will stop. I mean, they will start seeing an irreducible background that will be the end of the road for them. We also have such a limitation, our own neutrino floor. I'll show you where it is for direct experiments, fortunately much lower. Something else to be said about this is the fact that sometimes, I don't know if there's anyone from the LHC, I don't see any high-ending people here, well good, then I can speak freely. You know, if David Miller was here, he would show you plots where he would put the CMS exclusion limits all over the place here, and they don't belong in such a plot because they're very misleading. To do that, to put it in the same plot is very misleading. And the reason is that they are dependent on the mediator mass, on the mass of the particle, mediating the interaction in their case. So this is actually something from our latest publication where we choose some parameters and we show that actually they're complementary. Okay, for some bodies of the mediator mass, we're doing better than them, and for some others, they're doing better than us. But you cannot just plot things willy-nilly on this plot. This belongs to direct searches and at most indirect searches. And this is a plot I like by a French group that appeared last year, and I have tried to update it here. These people elaborated on the complementarity between spin-independent and spin-dependent searches. And these are supersymmetric models, and what you can see here is that, well, Lux may be beating us a little bit here. There's still some models in there that we are not probing anything to the right of our line is excluded, anything above their line is excluded, but we are almost there. What makes the difference here is not that they achieve a lower level of background for a certain detector mass, is the fact that in the spin-independent coupling you have an enhancement to the cross-section that goes with the square of the number of nucleons. And that will be the subject of the second part of my talk. That's what we call coherent scattering, and that's what's expected to be happening there. It's a process that we have not seen yet. It's standard quantum mechanics and a prediction of the standard model, but we are hoping to see it at least for neutrinos. Okay, but that is why the spin-independent searches are a little bit advanced even now with respect to us. Not much. The distance is close. And it should be kept in mind that this is a choice of supersymmetric models when theoreticians or phenomenologists choose their own flavor of supersymmetry. This stuff is all over the place, so clearly there might be some models where we're performing better than liquid signal and vice versa. Now, PICO 60 is not out to pasture yet. This is something that I should probably not be showing you yet, but this is our recent result in spin independent, and we already have data that allow us to push down to lower masses. What we did here was actually a very patient labor of changing the pressure in the detector and essentially riding that curve that I showed you before. There we go. We essentially finagle with the threshold, watching the increase in response to environmental gammas, and we stopped when we were seeing just 1 gamma per day. And we've been running for a few weeks, a couple of weeks, and what you can see is that we're already extending the sensitivity to lower masses. So there's an ongoing lower threshold run, and this will eventually be published very soon. If you plot the same thing in spin independent, it essentially matches the sensitivity of supersymmetry, the present sensitivity of supersymmetry. So this progress that we wrote about in the recent Kavli proposal is something that is happening already. We're delivering the goods even before we get a decision on that proposal. Now, if I join the dots there, and you can argue with me, and I'll be glad to wrestle you to the ground, I see a concave and a convex curve. Is anyone willing to disagree? And this is what you get from 7 extra orders of magnitude in electron recoil rejection vis-a-vis liquid xenon detectors when you compare apples to apples. These are their couplings to spin-dependent couplings to neutrons, where they excel, and our spin-dependent couplings to protons. You can see that the progress rate for liquid xenon is lower than ours. Adam Soneshek, who came up with this plot recently, and I dropped this plot, he was very conservative because this detector here that I'll say a word about in a minute is actually being built this summer We expect to run it for 10 months, so I would say that our results, whatever they might be, we might run into trouble, but if everything goes as planned, we're going to be right here. PICO 500, the proposal is out. It's a Canadian proposal. What DOE has achieved with their wisdom recently is to turn PICO into a Canadian experiment, but let's not go into that either. PICO 500, if it gets funded, we start actually buying things for it this year, this summer. Okay, so this is very conservative, I believe. And oh, the animation worked. Oh, sure. So this is for Mike Chrysler, the inventor of our next next design, the so-called right-side-up chamber. This is what we're going to be doing from now on. Up until now, we've been placing a buffer liquid, as we call it, water typically. In some experiments that we did here in the early days, we used alcohols for some other compounds. But anyway, we put very clean water on top of the refrigerant, and these two liquids are very immiscible, but not completely, unfortunately, but very much so, millimoles per liter. This is all the way they have into each other. And we are reverting things around. Why do we want to get rid of this poor water here? Well, it's been giving us all of these problems we've had in the past. For one thing, some of these liquids, it can lead to acidification that we have measured, oxide particulates raining down from those bellows. And there's a reason to have the water in there. You don't want to have any refrigerant wetting the rough metal surfaces. You would have boiling all the time, like in the old bubble chambers. But Mike came up with a wonderful design where you reverse things, you turn them upside down, and instead of having a water piston, what you have is another silica piston, and you compensate for things with a thermal gradient. Essentially, this volume here that is wetting the metal quartz is cold to the point that it is in the liquid phase, and this is superheated. Now, that's not going to run. Okay, but I was having problems with PowerPoint, and I'm very stubborn, so PowerPoint, my ass, I'm going to show you that movie. I'm going to show you that movie because the graduate student who did this are Ortegas in the audience. Anyway, things work as expected. These are console simulations that Aaron is doing, where we already know what kind of power, cooling power you have to put here, and heating power in the plates, etc., in order for this thing to run. Take that PowerPoint. And oh, by the way, this thing, as I said, is already being built. The internals. Rock is not in the room. It's a shame that Dean is not in the room, because the original plan was to build all of these internals here. Oh, but I have him in the room, Steve. But since we don't have a shop anymore, this actually had to be, outsourced. Okay, and done at Pacific Northwest National Laboratory. But anyway, things are coming along, even though we're not getting a lot of local help. I have to put that in. You can tell wrong what I said. And this is the ultimate chamber for us. This is PICO 500. As I said, we're about to hear from this Canadian proposal. We think we're in a good spot. Certainly the project has a lot of support in Canada, and we have a lot of collaborators there now. But PICO 500 essentially should have a similar reach to LC. But my money is on the fact that we're going to get there much earlier. Steam dependent. By then, we will have probed essentially all of the supersymmetric models that one can think of through this coupling. Okay. This infrastructure here, by the way, is already in place. This is not something we have to come up with. We're taking possession of the mini cleaning tank. So this is really all we have to build, and it's essentially a slightly larger version of the, not much larger version of the PICO 4L chamber. Okay, next subject. We have just about enough time. Can you strangle a neutrino detector? That's more like what Juan showed here. One of our grad students is doing. This is Grayson Rich, who's our new Fermi/KICP fellow this year. And we are in the so-called neutrino alley the spallation neutron source at Oak Ridge National Lab. And I'm going to claim that this thing is the smallest neutrino detector ever built. So it is. That thing detects neutrinos. Okay? Now, in principle, the answer should be in the affirmative. If you look at neutrino cross-sections, in this case for argon, the largest one by far, especially at low energies, and this gets exacerbated if you're dealing with a heavier nucleus like ours, should be the coherent, what people call coherent elastic neutrino nucleus scattering. And that is a mouthful, so I'm going to call it sevens. I'm not so fond of this terminology, but certainly in collaboration meetings, you don't want to say coherent elastic neutrino nucleus scattering, we just say sevens. So when you hear me say sevens, I'm talking about the same process that we expect to be happening from WIMPs when they interact with nuclei, if that's what they do, but with the projectile, the incoming particle being a neutrino. Okay? So this is, I'll show you a cartoon in a second, but this is essentially the way we expect WIMPs to interact as well. And the same coherent enhancement to the cross-section is at play here. What you have is a cross-section that goes with the square of the number of neutrons in this case. When you're dealing with neutrinos, for WIMPs, it's typically the square of the number of nucleons. Okay? These, by the way, I don't think well, maybe for argon that might be the case, but coherence is something you lose eventually. And this trick only works up to a few tenths of energy. If you come in with a faster or higher energy neutrino, the coherence enhancement to the cross-section will soon disappear. So yes, you should be able to miniaturize neutrino detectors for low energy neutrinos at least. And you may be wondering, why is it that we haven't done that? Well, because it is very tricky to come up with the right combination of neutrino source. There's only a few available that can give you neutrinos in the right range of energy to see coherence over nuclei, and detectors. The detectors are essentially dark matter technologies. We're looking for the same low energy few keV nuclear recoils here. So there's a lot of overlap between both fields. If you look at the first paper to mention CDMS detectors, silicon bolometers by Cabrera and company, I think I have the paper later on in another transparency, it doesn't mention dark matter once. It talks strictly about coherent neutrino nucleus scattering, and then later on it was figured out that it was easier to look for dark matter than to look for sevens. So that kind of sums it up. But the process was proposed some 40 years ago, and we haven't been able to come up yet with the combination of neutrino source and neutrino detector able to exploit this largest cross-section for low energy neutrinos. In the interim, over these 40 years, people have come up with a lot of applications for sevens. If you show that you can measure sevens, you can do all sorts of wonderful looking for deviations from the standard model due to a finite value for the magnetic moment of the neutrino, due to non-standard interactions of the neutrinos with quarks, so on and so forth. This is an old transparency that I should update because essentially there is one such paper, phenomenological paper, proposing how to do something new with sevens once per month. Okay. And that's been going on that trickle has been going on for about 40 years. People have even daydreamed of the day when we actually can develop some neutrino technologies because we have miniaturized the detectors to the point that we can use them for reactor monitoring. We can do searches for sterile neutrinos. This is a neutral current process, so it should in principle work as regardless of what flavor of neutrino is responsible. So if you were to see deviation from the rate expected, it might be due to oscillations into a sterile, so on and so forth. There's really a very, very long list of these needs update. Now I know this is hard because I am one of these aficionados who's been trying to look for sevens for a long time, and every time I show this transparency, I cringe because this is probably the most miserable period of time in my life. This experiment we did at San Onofre. San Onofre is now closed for good, and I'm madly happy about that. But we spent about a year in the Tendon Gallery around San Onofre, where we got a splendid flux of neutrinos coming from the core the right image is to see sevens, and what we had there was one of the first PPC detectors, P-type 1 contact germanium detectors that we developed initially for this purpose. Coherent stands for Coherent Germanium Neutrino Technology. It's an acronym that has nothing to do with dark matter, even though we have used the same detectors for dark matter, similar to the CDMS story I just related. So we spent a year down there. When you get into the innards of a reactor, you start to see more people wearing assault rifles than hard hats. It is a fact. It's about 50-50. So it's a less than friendly environment. You cannot bring liquid nitrogen to operate your detector down there, so you have to distill it out of thin air. This thing is not meant, it's the kind of unit you see in your dermatologist's closet, but it's not meant to run 200 meters away from the ocean, as we figured, the hard way. Even the experimentalists in the room probably don't know about a device that I have in my lab where I can actually punch in numbers, connect to a telephone line, and open and close valves and interrogate the state of relays. So every interaction with this monstrosity here had to be done through a phone line. Usually taking camera images to see the status of different things. I mean, it was just horrendous. We had something like 15% lifetime, and we came close to killing the detector out of how many times. The truth of the matter is we achieved a really good background level, similar to CDMS actually, even though we're only 30 meters of water equivalent underground. And in order to do that, you required a triple level of active vetoing. You had an external muon veto, then an internal one, and then an anti-conductant large sodium iodide crystal low background around the germanium. Anyway, it was brutal. And all we got was this. This background could have been reduced. We later on realized that we could project surface events on PPCs. We didn't know that at the time. So imagine this background going down, but this is the noise in the detector that did not allow us to get to the seventh signal. Giorgio Grada encapsulated our progress as the first people to put the 7 signals on the backgrounds on a linear plot. So that's what we took home from a year of mystery. So it's hard to look for 7s, okay? We're not the only crazy people trying to do this. I'm just going to mention 2 contemporary attempts. They are ongoing. This one is from a fraction of the Super CDMS collaboration, trying to do this very, very close. Eventually they want to get 2 meters away from an experimental reactor at MIT using CDMS detectors. This is the paper that I mentioned before, and you see that it mentions 7s and it doesn't. In the whole paper, there's no mention of dark matter. There's also CONI, which is a variation of DAMIC. These are the detectors that Paolo and Juan Strada and company are using. They are running next to a reactor in Brazil. I think they are more of a competition than Super CDMS, especially with the latest advancements in, I don't know if you heard about the Skipper readout, but they have recently achieved single electron sensitivity, which means a 0 threshold. Essentially, the whole coherent signal could appear in their detectors. So, this is a serious attempt, and I'm sure that they will eventually see 7s. And there's more. I've been telling you about attempts to see 7s in reactors, but there's just 3 types of neutrino sources you could invoke that where you would expect to see some coherent scattering of nuclei. Stuff coming from electron capture sources. You need very intense ones to do that. To my knowledge, nobody has tried, even though they exist and they have been used to calibrate solar neutrino detectors. Reactors, that's us, the MIT reactor, experimental one, and the SNS, the spallation neutron source at Oak Ridge, the most intense neutron source in the world. We take it even though it's not a neutrino source. Why? Because, well, it was not intended to generate neutrinos, but the main job is to generate this many per day neutrons. We get about a factor of 200 over. So there's a lot of neutrinos coming out of that, and we want to parasitically use those. What's beautiful about the SNS, well, let me tell you something first. It's it's not like this is much easier than looking for sevens in a reactor because there's a quid pro quo at work here. I'm about to mention that this is a pulse source. In a reactor, you just have a flux of neutrinos streaming through your detector. You don't know when the signals are coming. At best, you will have to wait until the reactor is off to get a background measurement. But here you know exactly when they're coming at you, on cue, okay? 60 times per second. However, the flux of neutrinos at an espallation source, even the most intense ones in the world, is on 5 orders of magnitude lower than 20 meters away from a reactor. So you have a price to pay. The recoils are also slightly higher in energy, so the specs on your detector threshold are not nearly as high. So it's not a panacea, it's just different. It's a different set of problems. We're part of a collaboration that we call Coherent for total lack of imagination there, where we're trying to use different types of detectors. This is one that they had a liquid argon detector, they had a Fermilab, and it's already installed and not working so well, I should say. We have several tons of sodium iodine that will be eventually used for sevens, but at first we're going to use them to study a higher energy neutrino process. And then what we've been running for 2 years, which is our detector based on cesium iodine. Eventually we want to measure sevens with more than one target. We want to see the dependence on n squared, on the number of neutrons squared. We want to see the timing characteristics of sevens. The seven signal is not only characteristic in energy, but also in time, so on and so forth. We have rapidly populated this, what we call the neutrino alley, with a number of detectors. That's the cesium iodine crystal I'm going to tell you about. We're in the primo spot. Actually, this spot here is where you have the lowest neutron backgrounds, and also, of course, the highest neutrino flux because you're the closest to the source. Notice that I mentioned the fact that this is a pulse source. I said, well, this is advantageous. You know when your signals are coming, you can have almost 4 orders of magnitude of background reduction. Well, the problem is some of the backgrounds are false as well, okay? So what works for us is the fact that these 20 meters are iron, essentially this monolith is mostly steel and iron, and then concrete and gravel. So whereas we have 10 to the 22 neutrons being produced per day at that point, 20 meters away, we get to see 1 neutron per day where we are. We have measured this, but a big part of the effort within the collaboration, the European collaboration is being monitoring and characterizing neutron backgrounds with really fancy neutron detectors brought by our collaborators in national labs. I will tell you, I'm going to run to finish within 5 minutes. This is all stuff that is published, so I won't elaborate, but there are reasons to choose the material we chose. Cesium iodine sodium doped. It is an inorganic scintillator. It's been used whenever thallium doped to look for dark matter by several groups. And it has several advantages. One of them is, of course, a large cross-section. Cesium and iodine are heavy. The fact that they're very close in mass makes our life much easier because at some point you need to study this so-called quenching factor, essentially the response to nuclear recoils rather than electron recoils. And if you have 2 recoiling species, things get complicated very fast. So these 2 react to the incoming neutrinos essentially the same as you can see in this plot. And there's a lot of advantages. I mean, I waxed poetic in this paper, but I claim, for a good while that this was the way to go, and I think we're going to be proven right very soon. There's even a small detail. The choice of dopant is actually criminally important. If you were to use thallium doped cesium iodine, which is the standard material, then in an experiment next to the surface, you would have an afterglow level that would essentially swamp your signal. Where next to the surface, so muons galore go through the detector, and each one of those produces tens of millions of photons, and then a long-lived afterglow tail. You would not be able to do this with thallium doped. We have to use the right dopant in the scintillator. Anyway, we did our homework. I don't have a photo of Nicole Fields here, the first grad student to work on this. Her thesis is essentially all of the background studies done with this 2-kilogram replica of the actual neutrino detector you already saw being strangled before, and we showed that if you build it, it will work at the SNS. In the laser lab, we actually have the same algorithm as we have in the SNS. And as we expected, it's no surprise, but when we finally built the large crystal, we got funded by the NSF to do this, and we built the large crystal, and we actually have a lower background at the SNS that we measure with the smaller device here in Chicago. We did preliminary studies of neutron backgrounds, the ones that are associated to the beam, and I need to rush a little bit. What we determined essentially is that we have a signal to background of the order of 20. We have 20 times, 21, 25 times more sevens signal than the two backgrounds that we can name associated to the beam activity. These are neutrino-induced neutrons in lead. It is the same process that the HALO project running in Snow Lab is exploiting, or hoping to exploit one day when the next supernova goes off in our vicinity. We're measuring that cross-section for them, by the way. I promised some examples of what I think I've mentioned already, some examples of exchanges between technologies between these two fields, but here's one. When we brought this original shield that we, by the way, in this preliminary studies of backgrounds, we realized we needed to add some internal neutron moderator to knock this down. So we were left with a very nice shielding with a very efficient mu veto, etc. And that's been running, that's been recycled, and it's running in the laser basement where you have a primo spot, an ideal location to look for strongly interactive massive particles. And there's some real contra natura things going on down there. I've been granted access. We're in one of those for while the building was being upgraded. We're cooling PMTs down there inside the shield, which is something I don't want to be doing anytime soon again. But it's working. We've been knocking down, I'm using the royal we. I'm doing this sort of. But anyway, this is a vice of mine these days. I just like Sims. There's a lot of face space there that nobody has bothered to check on. It's mine. And anyway, there's a lot of things that you can do with an old shield and old detectors. These are the same detectors that were used to do this characterization at the SNS of the neutron backgrounds. And there's been a lot of progress in knocking down backgrounds and even more progress to come. I'm hoping to finish this off by this summer. It's been tremendous fun. Studies of the response of the large crystal to radiations so that we can build libraries of events on which we can train our cuts to the data. This is the work of Juan. He's been slaving over data analysis for the last 2 years almost. The crystal has an excellent light yield and uniformity. It's by design. You can see that essentially the light yield doesn't change with the long distance of this crystal. We've been out places measuring the quenching factors, the response to low energy nuclear recoils over the region of interest for sevens. And within the collaboration we have essentially reduced this to about a 10% uncertainty. And these pictures, you've seen this installation a year and a half ago of the detector. We've been marching along. This is the original studies of neutron backgrounds. This is the cesium-iodine crystal running. These are all the detectors studying neutron backgrounds. One dedicated to characterize these neutrino-induced neutrons in lead, measuring the cross-section for HALO. And this is the end of my talk. I think I have just 2 more slides, and this is the plot that I wanted to show you. I cannot show you the money plots. I'm going to show you something where data is data when the SNS is off. About 2/3 of the time, the beam is on producing neutrinos. This is the 1/3 of the time when no neutrinos are being produced. Okay? And what you see here is a residual. Every time the SNS gives us a POT, hot signal, protons on target, we take long traces where essentially what we have is a measurement of, after the POT signal of maybe a sevens interacting with the crystal. Before, what we have is a measurement of background, done for free. We apply the same cuts, and if the SNS source is not on, you expect to see the same levels of background in both the pre-trigger and post-trigger trace. Okay? So this is what you see here, oscillations around 0. The beam is on, there shouldn't be a signal, and there's none. You see the projection on energy and on time. Okay? The 7 signal is characteristic of both. This is where we're going to be this August. That's the standard model expectation. Okay. The error bars are a little bit different because there's two times more data, but this is where we are, and yes, we have analyzed the input data. But okay, this is what you see today. These are the contributions. Remember, I told you that this is a neutral current process. These are the contributions from the three different flavors. This is a stack plot, so this is the contribution from that. The difference is the contribution by those neutrinos. So we'll probably be able even to demonstrate that that you cannot do without one of these neutrino flavors to explain a signal in this field. And the next thing we want to do is precision studies. This CC-MIO line has enabled us to get to the point where we might be able to measure the cross-section with maybe a 20% uncertainty, but we're not going to be able to do something much more useful than that. If you want to do the new neutrino physics of interest, deviations from the standard model, you need something more sophisticated. And this where again we get a little bit of cross-interaction between fields. What we plan to do is to put 10 kilograms of germanium in a compact form of 4 detectors. Something we can do because of the research on within Coherent C4. And what we're doing also is measuring the quenching factor for germanium to depth. These are 2 sets of measurements. The band is actually a measurement, not a feed to the data. These are measurements we did here as well. And within 2 months there will be, this is kind of crazy, but there will be 4 more measurements of this quenching factor from within the Coherent collaboration in germanium. We want to know these quenching factors so well that if we ever detect a deviation from the standard model prediction, in this case from a finite value for the magnetic moment of the neutrino for a different target, if we ever see that, we will know it's because maybe we saw new neutrino physics and not because we haven't studied the quenching factors well enough. Okay, so that's the nitty-gritty. That's the big effort that goes up front before you can do physics of interest. C4 is running, by the way, in Sudan for a year and a half. It's been running. We will have results eventually after August when we stop it. The Sudan underground laboratory is closing in. We have very, very nice new results. We essentially have matched the background of Majorana while still delivering a much lower threshold. Anyway, something else we plan to do is bring a new technology. This is the last slide. I'm done. Something we plan to do is bring a bubble chamber. Eric, I promised you to tell you something about Eric Dahl, our former KICP fellow, has pulled off something very important, something that Glaser himself failed to do. He's run at Northwestern a bubble chamber of the right side up design that we're adopting within PICO, where he's also capturing the scintillation. We have, all these signatures that I mentioned, including the acoustic signature, is also detecting the scintillation from signal. And what this will bring is a number of advantages for low mass WIMP searches, but also critically the fast trigger necessary to profit from the pulse signals at the SNS. With a standard bubble chamber, we cannot do this. It's just too slow. You don't know, you wouldn't know for milliseconds where your signal is with respect to the process of the target signal. So he just needs about 10 kilograms of the stuff, and this will become a reality within Coherent. I should mention that Eric, and this is the last thing I say, received the presidential, let's see what it is, Presidential Early Career Award for Scientists and Engineers this year. This is the 2014 award that President Obama signed 1 month before he left office. So Eric gets to visit the White House this year. Thank you.
Thank you very much, Juan. Questions? Vito. Oh, you can eat it. Eat it.
What happens with the background that's in phase with your 60 degrees?
It is, I have waxed over a lot of stuff, but there's two kinds. The 1 neutron per day we get to see, that I mentioned because of the moderation of by 20 meters, and then the neutrino-induced neutrons in the lead, which we saw by putting neutron moderator within the lead. We have to redesign the shield. So one of them is 21 times lower than the 7 signal, the other one is 25 smaller. I mean, this is an argument we have to back up in our first results paper, but it's a very clean measurement from the point of view of signal environment.
So I was wondering, why are you building PICO 500 with that aspect ratio instead of something longer? Because it seems that the acoustic signals...
The short answer, because we have broken a lot of these longer chambers already. They are easier to break.
Okay.
And they're very expensive. The aspect ratio actually is educated by interactions with the manufacturers. There's fortunately a market for large synthetic silica vessels driven by the semiconductor industry. Otherwise, these things would be impossible to acquire.
But the acoustic signal would be good enough even at that distance.
If we ever see an acoustic difference between electron recoils and nuclear recoils, we're going to have to fold that into the design. And we're running out of time to do that.
Any more questions? Okay, let's thank Juan for a wonderful And we have a reception on the 4th floor, but first, against my